Let's talk about GZIP. You are probably familiar with .gz files. They are one of the most widely used data compression formats. macOS and most Linux distros come pre-installed with a GZIP program, which handles compression and decompression of .gz files. But not all GZIP programs are equal. For example, Apple's macOS is bundled with Apple's own implementation of GZIP, whereas for Linux it comes with the GNU version of GZIP. In fact, there are numerous other programs and libraries that will compress or decompress GZIP files, so in this video I wanted to take a look at a few of the options available and run benchmark of their performance. For the benchmark, I'm going to test two files at the opposite end of the spectrum. The first is the entire Linux kernel source code directly from GitHub. Since there are thousands of files, I'm going to create a single tarball file, which is 1.3 gigs in size. The file should represent a typical text data that is easy to compress. The second file I'm going to test is Ubuntu ISO image file directly from Ubuntu website. This file should represent a typical binary data that is unlikely to reduce size after compression. Throughout the video, I'm going to simply refer these files as the text file and the binary file. Most real data will probably fall somewhere in between. I'm going to run the benchmark on two different systems I have. The first is macOS running on the M1 ARM processor, and the other is Ubuntu running on Intel's 10th Gen x86 processor. The purpose of the benchmark is not to compare performance of M1 to the Intel's processor. The purpose is to compare different GZIP implementations and programs on a fixed platform. Alright, let's get started with macOS on the M1 chip. First, let's test the stock version of GZIP from Apple. This will serve as our baseline metric. For compression of the text file, it took 21 seconds and reduced the file size from 1.3 gig to 215 meg, which corresponds to the compression ratio of 6. With the binary file, it took Apple's stock GZIP 72 seconds, but reduced the file size only by less than 1%, corresponding to the compression ratio of 1. Okay, let's see how long it takes to decompress. For the text file, it only took 3 seconds to decompress, and for the binary file, it took 5 seconds. Now, let's see how Linux default GZIP compares with Apple's. I will download the latest version from the official GNU website and build from the source code with the default config. Okay, you can see this GZIP is now the GNU version. It took 22 seconds to compress the text file, which is 1 second slower than Apple's version. And it took 83 seconds to compress the binary file, which is 11 seconds slower. The file sizes are essentially identical to Apple's version, which is expected. In fact, every GZIP program I tested resulted in very similar compression ratio under the default setting. Now, the decompression speed was quite different. It took 7 seconds to decompress the text file, which is more than 2 times slower than Apple's. For decompression of the binary file, it took 17 seconds, which is more than 3 times slower. Now let's take a look at zleap. This is the go-to library if you want to add data compression support to your program. Python's GZIP module uses this library. Again, I'm going to download the latest version from the official website and build it from source code with the default config. It took 22 seconds to compress the text file and 75 seconds to compress the binary file, which is on par with Apple's version. For decompression, it took 4 seconds and 7 seconds, which is a bit slower. Next up is libdeflate. The author claims that the library is heavily optimized and significantly faster than zleap library. So let's give it a try. I'll clone the repo and build from the source with the default config. It took less than 10 seconds to compress the text file, which is more than 2 times faster than Apple's version. For the binary file, it took 53 seconds, which is about 35% faster. As for decompression, it took 2 seconds for the text file and 14 seconds for the binary file. This result is quite interesting because this library decompresses a text file 50% faster, but a binary file 75% slower compared to the baseline. So far, all the programs I have tested only support a single thread. Since modern computers are equipped with multi-core processors, it makes sense to run anything in parallel. For that, we have pixy, which is a parallel implementation of GZIP. I'm going to clone from GitHub and build from the source with the default config. Pixy by default utilizes all the available cores, which would be 8 on my M1 processor. With this, it took only 4 seconds to compress the text file and 14 seconds to compress the binary file, more than 5 times speed up from the single core baseline. However, decompression can't be parallelized, and thus it took 3 seconds and 6 seconds respectively, which is on par with the baseline. Okay, so here's the benchmark summary tested on macOS running on the M1 chip. The y-axis here represents the speed gain compared to the baseline, which is the Apple's stock version of GZIP. Interestingly, GNU's version of GZIP seems to perform the slowest, especially in decompression. zleap is comparable in compression, but a bit slower in decompression. Libdeflate is super fast in general, but somehow quite slow with decompression of the binary file. Lastly, Pixy has 5 times speed up due to parallelization in compression, but not on decompression. So what is my verdict? From the benchmark, my recommendation is to use Pixy for compression and use Apple stock GZIP for decompression. Now, I ran the same benchmark on Ubuntu running on x86, and this time it's more interesting here. The stock version of GZIP, which is GNU's implementation, is pretty much the slowest in every case, so I wouldn't recommend using the stock version of GZIP on Linux. Instead, use Pixy for compression if you have 4 or more cores to spare, and libdeflate if not. As for decompression, I'd recommend using zleap. Alright, hope you guys find my videos useful. Thanks for watching.